Okay. So last time we defined ancestral causal graphs, right? And I told you that this lecture, the next lecture, which we the lecture today, would be about representing all the all the graphs, all ancestral graphs that are equivalent in the sense that they imply the same condition dependencies. And this class is represented by another graph that's called partial ancestor graph. So we are going to define it. So it's just like a representation of all of the invariances in these ancestral graphs that are part of the class. And in the end, kind of in the middle of the lecture, I'm going to teach you the fast causal inference algorithm, or FCI algorithm. Is an algorithm that allows you to learn from observational data the partial ancestor graph, the class or the entire representation of this class of graphs that are compatible with the set of condition dependencies that are there in the data. Last time I told you that we defined this MAG, right? MAG is maximal ancestral graph, and I told you that some MAGs can be equivalent. They can imply the same set of condition dependencies. So, for example, and that there is a procedure, right? So to move from a causal diagram that's represented by a ADMG, that is a procedure to find the MAG. The MAG is already an equivalence class, remember, right? So many ADMGs are represented by the same MAG, but different ADMGs can kind of be represented by the same MAG as well, right? So not this, and then there is also the equivalence between MAGs. So in this example, we show different ADMGs. If you compute the condition dependencies implied by every either you can use this separation in the ADMG to see what are the implied condition dependencies from the ADMG. This is going to be the same as computing the M separations in the MAG. And if you check, they are going to be all equivalent. So let's see if I have here. No, but we can do, for example, a few examples. So V1 in this case is separated, or M separated in the MAG of V4 by conditioning on X only, right? This is also the same for this one, right? V1 and V4, you block these two paths by conditioning on X, so this is also M separated.
And so is that also the reason we don't have a connection from V2 to V3? Because the way, because if I remember correctly, we had a definition somewhere where it said that we have like
reduced path.
I'm not sure whether we have a connection from one graph to another if one is the parent of the other, but not the other way around. Maybe I'm also applying the wrong definition right now.
So the maximal ancestor graph represents all the ADMGs such that every edge is an inducing path in the ADMG. An inducing path, the simplest one, is an edge, right? So if you compute if you apply the procedure between X and V3, here we don't have an edge in the ADMG, but that is an inducing path that makes this edge being in the MAG. And then you orient the edge by following ancestrality. Maybe that's what you're talking now. So X is pointing to V3 because there is a directed path from X to V3. So the representation of a maximal ancestral graph is a representation of all the ancestralities and non-ancestralities. So the arrowheads means non-ancestral, while the tails means ancestral, and the existence of an edge represents an inducing path in all ADMGs that are part of this MAG.
Then I maybe haven't quite understood yet how that applies. Why? So just in this example, why is V2 not? Why is there not a directed way from V2 to V3?
Because the V2 is separated from V3 in this graph. So that exists as a conditioning set that makes V2 separated of V3. So first there is no edge. You can see there's no edge. And also there is no inducing path. An inducing path would be, in this case, if I put a bidirected edge between X and V4, then it would be an inducing path. But we don't have here. By conditioning on X, you separate, so you block the path V2, X, V4, and V3 through this directed edge, and also through this bidirected edge by just conditioning on X.
Okay, yes.
Right, so there is a way to separate, so there is no inducing path.
Okay, yeah,
right?
That answers my question.
And then this is not represented. This is represented actually by a missing edge, right? So missing edge means that there is no inducing path. Edge means there is an inducing path in every ADMG that are represented by this mag. So many DMGs can be represented by the same mag, and different mags can also imply the same conditional independencies, right, through M separation. So if you compute all the implied conditional independencies, which are those implied by M separations in all these three graphs, as an example, you see that the set of M separations will be the same. So they are called Markov equivalent mags. I want to ask if there is a condition. So if you look at these three graphs, one thing that you can, maybe I can ask you, is this 2 or 3 mags are Markov equivalent or not? This can be a question that I could ask you. The first attempt, which would be like brute force, would be like compute all M separations in all of them and see if there is any disparity. If there is, then they are not part of the same equivalence class. If they are imply the same M separations, they are in the same equivalent class. But this can be kind of burdensome, right? So it can take a lot of time to actually compute all M separations. In these cases, they are simple graphs, so maybe you find it easier to compute the condition dependence, implied condition dependencies, and see if they are equivalent or not. However, this is what I'm doing here, right? So for example, W and X, they are separated by conditioning on nothing, right? By the conditioning on the empty set. So if you get any of these mags, you see that there is all the paths are already blocked because there exists a collider. So you don't need to condition on anything. The path is connecting W and X are blocked. So they are already M separated. Another set is this one. W is M separated from Y given Z. W and Y is there. So you see that there is this directed, path with this directed edge here. So this is open. When we condition on Z, this is blocked. And that's fine that we are opening this collider because the other collider is still intact. So W and Y are M separated just given Z. You can see this here. You can see this also in the second and not in the third. So you see that there is a difference here. So when I condition on Z here, I open the collider, but the X is now not a collider, so this path is open. So the set of minimal, so there is this notion of minimal independence because it's the minimal set that we find to separate the path. A lot of definitions. We see that the set is different. So this independence, W and Y given Z, in this graph, they are not independent. So that is a difference. So by looking at those, you see this, I think it is not more. Yeah, so just looking at the set of implied independencies, you see that the first two are in the same equivalence class, while the third is not. Okay? But there is a theorem. So remember that in the causal sufficiency or in the Markovian case, we have that the theorem that says that if there is the same skeleton and the same colliders, the same unshielded colliders, then the graphs they belong to the same equivalence class, right? So the DAGs represent the DAGs because it's without latent confounding. they belong to the same equivalence class. We have an extension to this case where we have latent confounding, right? So the theorem applies to mags. So we have to convert a DMGs to mags so that we apply the theorem. And the theorem says it's kind of similar, but we will have a difference. So two mags are Markov equivalent, or they imply the same condition independencies if and only if they have the same skeleton, same thing as before, but the same colliders with order. So we need to know a different notion of collider to discriminate the class of the mags. You see that in this case is this two, the X here is going to be a collider with order because the X in this case could be learned as a collider after conditioning on Z. You remember, right? So once we condition on Z, we know that this has to be a collider because otherwise the path would be open like the third mag here. So if I could see independence just conditioning on Z, is because the other path has to have a collider. That's why I could discriminate the X as a collider. And this collider is of order 1 because I have to condition on one variable first to see that it's a collider. So that's going to be the notion. We are going to define it better. You see that X here is a collider with order. It's different than this collider, X, Z, and W. This is a collider of order 0 because I don't need to condition on anything to know that this is a collider. The Z is a collider. Basically, I know that W and X are independent given anything, right? So the conditioning set has length 0, or the size of the conditioning set is 0 because it's the end. So that's why the Z here, this triplet, is a collider with order 0. That's kind of is going to be the notion.
What about the Y then? If you take the long path, the WZYX path, Y is also a collider for that path, right? What kind of order would it have?
So there, you don't know, because since this is a tail here, when you condition on Z, consider the two possibilities. If this is a tail, you condition on Z, and doesn't matter what's there because you blocked. If it's not a tail, it's an arrowhead, then it would be open, and then you would be able to classify the Y as a collider or not by conditioning on Y or not. But once you condition on Z, in this case that it is a tail, can be a collider or not. Both cases would work because it's already blocked, right? So the Y there is not a collider with order. It's collider there, but doesn't need to be. So there are colliders. They could be even invariant in the class, but it's not a collider that you consider as part of the theorem. So you can understand that this is actually a collider that's discriminating the class. You'll see more examples later. Yes. So, as I told you, X is a collider with order 1 in these two cases here. But to define collider with order, we will need this definition of discriminating path, which is kind of the idea that I just explained to you. It's a path that's going to help you to discriminate whether the X is a collider or not. It's going to be always a discriminating path for a variable, in this case X. So definition of discriminating path. So in a mag, so that there is this path, it starts with X and Y, and it's going to be discriminated for the second to the last variable. In this case, they're V. So there is a path, and the last to the second is going to be the one that I'm going to discriminate it, right? So it's a discriminating path for V in this case. First, this path has to include at least 3 X. Then the V has to be a known endpoint and adjacent to Y. It's the same as the second to the last, right? So cannot be the last variable, has to be a known endpoint, so in the middle, but it has to be adjacent to y, which means that's the second to the last. And x and y cannot be adjacent, so they have to be separated, because that's where we started with. We saw that x and y are separated given some set, and then you see that the variable that we're trying to discriminate is either part of the set or not, depending if it's a collider or not. Okay? So x and y is the pair of variables that we are trying to separate and then discriminate for v. And this path, it's important now. Every vertex between x and v is a collider between x and v, okay? And then we are going to see what's happened with the y there. And all these colliders have to be a parent of y. Let's see an example. This is an example. Basically, this path x, a, w, v, and y is a discriminating path because first it has more than 3 edges, okay? Second, the v is the last to the second in the path. All the variables from x to v are colliders. The colliders are parents of y, and this is going to be now, we are going to use now this criteria to discriminate what's going to be the v here. And the idea is the one that I just explained. If v is part of the separating set of x and y, then means that this is a non-collider, because I had to condition on it to separate the x and y. Because when I condition on a, which is necessary because a is a parent of y, I open the collider in this other path. Then again, that is the w that I need, because this path now is open. This path x, a, w, and y is now open once I condition on a. So I have to condition on w again. And when I condition on the w, the second collider opens. And if I have the separation already, then it's going to be the second case where v is a collider, right? So if v is not part of the separating set, then it's a collider. But if I have to add the v to see the separation or the independence, then it's a definite non-collider. So because it's a definite non-collider, we are going to put even a tail here. We are going to see, if there's time, we are going to see the proof of this. But basically, I know already that v is an ancestral of y. Here can be anything. So that's why there is a circle. Could be an arrowhead or could be a tail. But I'm sure that this is not a collider, right? So if you put the arrowhead here, it's still a non-collider. If it's a tail, it's still a non-collider. But definitely non-collider.
Can it be the other way around, where the arrow pointing from v to w, v to y has a circle?
Sorry,
That's
how?
for the separation set xy, so the top right one.
Mm-hmm.
So from v to y, instead of having a straight, instead of just having a tail, we have a circle. And then where the circle is, we have a tail.
You're trying to move this like this?
No, I'm trying to flip the circle and the line. Yeah, that one and that, like you flip that. You swap those two. That's the circle and that's the line.
So you see the proof why this cannot happen?
Okay.
Basically, it's going to either violate, some of these properties of a maximal ancestral graph. Either it's going to form, so you can see by choosing all the possibilities. So suppose that this is going to be an arrowhead. So if it's an arrowhead, then since this is not a collider, this has to be a tail. And then this is a tail and an arrowhead, then this is a tail already, then this is what? An almost cycle. So you cannot have an arrowhead here. So basically you can prove by contradicting all these possibilities that you're trying. And you see that this is definitely an ancestral relationship. Remember that this is a MEG. This doesn't mean that this happens in the ADMG. In the ADMG, I could have a bidirected edge here, but for sure, V is an ancestor of Y through a path like here. Maybe with time we will get this feeling, but there are cases where because the edge in a mag means that there exists an inducing path, and a bidirected edge is an inducing path. So the edge exists, and the direction means that there is a directed path from V to Y. So if there is a bidirected edge between V and Y, I'm sure that this has to be like this, because otherwise it would form a collider. So in all the possibilities, V is an ancestor of Y, and this is what we are representing in this graph, which is kind of already a peg here, because you see, I'm introducing the peg without showing the definition, but it's to create this intuition.
Also, what does discriminating mean in this context? I kind of only know it like...
Discriminating is kind of discovering. So you are trying to differentiate. Differentiate is different.
Okay.
Differentiate something in mathematics. Like you are trying to see the differences. So it's discriminate. This is a word, and it's showing the difference. So we are discovering if V is either a collider or not. So the path is the responsible for me to know if V is a collider or not. Okay?
Yep.
Questions about this?
I guess one more question. So how do we know if V is in the separating set or not? Because here it's just kind of, I mean, those are just the two options. Is it just based on the graph, or?
Yeah, we are going to get there. So I'm giving you the graph, so you know how to identify a discriminating path in this graph. And this is going to be useful later when I'm going to apply the theorem. Later, the discriminating path is also a pattern that you use to learn this from data. So this definition of discriminating path is going to be used for more than just the theorem. So you will see at least two applications in this lecture. But for now, it's given. I'm giving you the whole graph, and you identify if it's a discriminating path or not by checking if it's a collider path, where all the colliders are parents of Y, and then the variable V kind of, that is only one way of behaving because of this pattern. Understand? Let's see next the definition of triplet with order, because maybe this is going to help you. So the definition is a recursive definition. It's kind of an algorithm. It's like an algorithm that is going to define what is the triplet with order. But maybe I give you the intuition, you don't need to kind of follow. First, triplet of order 0 are those such that forms an unshielded collider, as the ones that we saw in the Markovian case without latent confounding, right? So it's a triplet, and A and C are not adjacent, so this is already an unshielded triplet. And we are just talking about triplet with order. I'm not saying if it's a collider or not, but it's unshielded. So that's going to be of order 0. That's all you need to know, because they are already separated. So since it's just 3 variables, and the variable in the middle, like either you condition on the variable or you don't condition on the variable in the middle. So basically, the discriminating case has the set has size 0, which could be the empty set or the one that we're looking for. But basically, it's the first case where you start. Then the triplet of order 1 can be first. I think it's better to read directly here. So first, it's going to be described by a discriminating path, right? And all the colliders, because since the discriminating path is a collider path, all the colliders in this discriminating path has to be with lower order. So that's what's written in this cases here. So if you parse later, you see that this discriminating path that has X, then a lot of variables in the middle, those are going to be the colliders one, Q1 to QP. Those are going to form triplets that has to be of lower order, not necessarily 0, so just lower order, and is going to discriminate for B, right? And the last, so this is just defining the last triplet. So the last triplet, where QP is the last one here, basically you can just flip, right? So it's either QPBY and YBQP, so it's just saying the order doesn't change. What's talking about here? That is a discriminating path for either tau. Okay, so it's just discriminating B given this triplet. So we are talking about the triplet ABC, right? So in the beginning, a triplet ABC belongs to order 1 I plus 1 if these two things happen. And the triplet that has order is ABC, which is the last one, right? So that's what the definition is telling you. But the intuition is what I told you before. So in this example, maybe I will ask you, what are the triplets that are forming the triplets of order 0, either collider or non-collider? So those, first definition, a triplet belongs to order 0 if just A and C are not adjacent. A, B, C is a triplet. They just need to be unshielded. So what are the triplets that are unshielded in this case? ABE. ABE is a non-collider. So it's going to be a triplet that has a non-collider of order 0. Non-collider of order 0. ABC, ABC, AB, BE, D. Also, there are many. Huh? BCD, BCD. So basically, anything that's unshielded, the variable in the middle is going to have order 0. Okay, but could be collider of order 0 or can be non-collider of order 0. But has order 0. Now, the order 1 kind of, I prefer the intuition. You need to condition on first one variable to then detect the variable of the triplet that I'm talking about. I'm going to give you an example just because it's the first example for you. But let's talk about the triplet BCE. Okay? BCE. BCE is going to be, I know that there is this formation here, so the BCE can only be a non-collider because when I condition on B, I have a path that's open. And you kind of know that this direction here is blocked. So the only possibility is that this direction is open. So the only way is that this is a non-collider. So to discriminate the fact that C is a non-collider, I had to condition on first one variable, which was B. That's why the C is going to be in the triplet BCE is going to be a triplet of order 1, because I condition on one variable, and in this case is a non-collider of order 1. What about the triplet CDE? Can anyone tell me? We can follow the definition. So in the first, when I explained the BCE, I kind of gave you the intuition, but let's apply the definition. The definition says so first, this is a triplet that I'm trying to say if it's with order or not, and it's part of this path A, B, C, E, where it's a discriminating path for C, because it's the second to the last. Everything from the beginning to the first, to the variable is a collider path, so all the variables are collider. The variable is also a parent of the last variable. And I know that's, so this already makes this as a discriminating order, a collider, a triplet with order. But I know that's a non-collider by the fact that by condition on the first triplet here, this path is definitely, and I need this to separate A and B. So I always start with some variables, a pair of variables that are separable. So these two variables are separable because I condition on B. And then when I condition on B, I am forced to condition on C as well. This is because the discriminating path is telling me this. The C either is part of the conditioning set or not. So since it's part, it's going to be a non-collider. And because I could find this discriminating path in this graph, this is a non-collider of order. And since I conditioning on one variable to find out if it's collider or not, it's of order 1.
C is of order 1.
Now I'm talking about the BCE. Now I want you to see what happens with CDE.
Order 2.
Order 2, and it's now a collider of order 2. Right? Because again, that is a discriminating path where this is the last triplet. The variable D is not part of the separating set of A and E, right? Because I had condition on B and C to make A and C separate. And then I know that this is a collider because D is not part of the conditioning set. Okay? I have here the table of all the colliders and non-colliders with the order in I. So you told it's easy to find all of them that have order 0, so they are unshielded triplets. We discussed about the BCE that has order 1, and we just discussed the one that has order 2, CDE. Those are all colliders and non-colliders with order that we have in this graph. It's a bit hard to find in the beginning this discriminating path, but you are going to get used to it. Let's move. Now we are back to these 3 examples from the beginning. I told you that 1 and 2 are in the same equivalence class, while the third is not.
It's relevant to the previous because of that I interrupted.
Sure.
What's the difference between collider or of order 0 and collider of no order? This is what I cannot understand.
Oh, it's because collider of no order is because there is no discriminating path between them.
For example, in this figure,
For example,
there is no
BEC. What do you think about this collider? Let's do the exercise together. First question, is there a discriminating path where CEB is the last triplet?
No, because E is not a parent of C.
So it has to be a path between 2 separate variables, first of all.
And the problem there is B and C are adjacent, right? That's
Yeah, so this cannot be the pair that we start with. Let's try A and C. See, they are separate. That's why I started with triplets. So that's why there is this rule that says that all the triplets that are in the path are of lower order. So we have like those that are already separate. So A, B, and C. So path is between A, B, and C that includes A, B, E, and C. It's not possible. So you need a path that starts like this one, right? So A and C are separate, and B, E, C is the last triplet. It's one path. But the path has to be with all colliders, but this is not a collider, so it's not a discriminating path. Which other path could have maybe this D, C, E, and B? So B, E, C is the last triplet. B and D are separate, but then C is not a collider. So you need to find this collider path, and all the variables that are collider are parents of the last variable. So you need to find exactly this kind of situation.
What was BED? Because I think the order was written as 0.
All right.
I cannot see the discriminating path.
No, but 0. So it's unshielded. So there is no variable, no edge between B and D.
Yes.
So BED is an unshielded triplet. And by being unshielded is of order 0.
Oh, okay.
Because when you have an unshielded triplet, you have two situations. Either the variable in the middle is part of the conditioning set or not. If it's part of the conditioning set, it's a non-collider. If it's not part of the conditioning set, if it's not part, it's a collider. If it's a collider, it's part of the conditioning set. So you don't need to condition on anything before, or that's not the E variable, to start having this reasoning of adding the variable or not to the separating set.
So for unshielded colliders, we don't need a discriminating path to order. We can immediately say that without discriminating
Yes.
path, that the order is 0.
Yeah, you can think as you cannot say that this is a discriminating path, because the first rule of a discriminating path, it has 3 edges, but it's kind of the same feeling. So you know that basically you already have a separation, and you can discriminate if it's a collider or not by doing this test of it's part of the separating set or not. But you don't need to start with any conditioning set before doing it. But with the collider with order, you have to first start adding to the conditioning set to then do the test. So you can have colliders that are not with order, but the colliders with order 0 are different. So let's try to apply the theorem in these in these 3 graphs, right? I told you the answer. I don't know if you remember, but that is so. Let's try to find all the colliders and no. So first, I just need the colliders. I don't need to find the triplets with order. The theorem there just says that I have the same colliders with order. So I just need to look at the colliders. So what are the colliders with order in M1? So W, Z, and X is of order 0, and Z, X, and Y is of order 1. There are 2. So I have 2 colliders with order, one of order 0, of order 1, and that is this skeleton.
Sorry, which collider is order 0 and which one is order 1?
So the Z in the triplets W, Z, and X, so first is an unshielded. Unshielded, it's order 0. The X is not unshielded, so Z, X, and Y is another triplet of order 1, because I had to condition first on Z to then see that X is not part of the separating set between W and Y. So that is the discriminating path W, Z, X, and Y, where the collider is a parent of the last variable. So you see here W, Z, X, and Y as a discriminating path for X. Since X is not part of the separating set between W and Y, is a collider. So X is a collider of order 1 in the triplet Z, X, and Y. Got it? So what about this? So first, same skeleton as M1. Second, what are the triplets with the colliders with order? We need to, they have to be the same. So W, Z, and X is a collider of order 0, yes. X is a collider in Z, X, Y is a collider of order 1. Yeah. Is there any other collider with order? No. So you have the same set of colliders with order, same skeleton. So, I mean, maybe in this example it's harder to find the colliders with order and apply the theorem, but you can have now two different ways of detecting if M1 and M2 are part of the same equivalence class. So I know, just applying the theorem, that all the condition independencies implied by these two methods are the same, and that's why they are part of the same equivalence class. If we do this for M3, so skeleton is the same, WZ and X is a collider of order 0, but what about Z, X, and Y? It's not a collider of order 0, so the set is different. Is there any other collider with order? No. So it has one collider less than it was supposed to have. So it's a different equivalence class. It's part of another equivalence class. The ones that have only Z as a collider with order 0. Okay? So that is these conditions that we can check if two mags are part of the equivalence class or not.
Question for so like the triplets Z, X, and Y, they're not collider with order because Z and Y are adjacent.
So order 0 requires unshielded triplet. But all other orders, you won't have unshielded. That's why it's of a higher order. Because if it's unshielded, it's already the triplet with order 0. Now, if it's not a triplet, not an unshielded triplet, it can be of higher order. If that exists, is a discriminating path. So you never have the fact that Z and Y are separate, because if they were, this would be a collider of order 0. But they're a collider of order 1, because there is this discriminating path here.
So is ZYX a triplet of anything?
ZYY, no. That's a collider, but it's a collider that has no order.
No order, okay.
Because Z and X are adjacent.
Because Z and X are adjacent. That's the, okay.
Not only that, so it's not a collider of order 0, but also not a collider of other orders, because you cannot find a path. So first you need to find a path where this triplet is the last. So this can be the path, W, Z, Y, and X. But this is not a collider path. Like W, Z, and Y is not a collider path to discriminate Y. Was the first question for him, like if you're conditioned on Z, this can be anything, it's already blocked, so it's not discriminating the Y. Okay? So I have now another example. I just need to know if I'm late here. What do you think about these two mags? No unshielded collider. Is there any other collider of a higher order?
Discriminating path. These all colliders should be the parent of this.
Can you see any discriminating path? It's a collider path where all the colliders are parents of the last variable.
Oh, WZX.
E and Y, yes. So this is a collider path, a discriminating path for X.
For X, yes.
For X.
Yeah.
So, but there, the X is a non-collider with order I want the colliders with order, so it's not discriminating colliders there. So they are equivalent. X, W, Z, X, W, Z, and Y. X, W, Z.
Z isn't a collider though, in that path.
Yeah, no, yeah, and actually, I don't know, maybe you were talking about this collider being the collider path, but then Z, W is not a parent of this. So the fact that they have no collider with order, they have the same skeleton, and they also have the same set of colliders with order, which is empty. Okay, it's a bit tricky, but you can apply the theorem here and detect that both are in the same equivalence class by detecting that the set of colliders with order is empty.
So before discriminating paths, we should look for an unshielded collider first, because otherwise, if even there is a discriminating path, it doesn't matter.
It's true, because the discriminating path has to have colliders that are of lower order.
Then
So yeah.
increases the order.
Okay. What about this two?
There is an unshielded collider.
There is no unshielded collider. She's getting close to that. Yeah. So that is a discriminating path here, but the collider is not a collider of lower order, because there is no unshielded collider. That's exactly your.
Y is not unshielded because WX Y. Because there is no link between W.
Oh yeah, that's true. WX and Y is a collider of order 0, but here is also true.
Yeah.
True, yes. But yeah, is there any other?
No, this is
Yeah, because that's the other trick, right? So although that is a discriminating path for X, doesn't the definition of collider of the collider of order doesn't apply, because the collider of the path is not a collider of a lower order. So they are equivalent by, this is the set of condition dependencies, and they have the same skeleton, and the collider with order is the only one, the one that is of order 0. So the X there is not a collider of order 1. Okay? Okay. So basically, that is a definition of an object that's going to capture all these invariances across the mags, which will be these colliders with order and adjacencies. So a partial ancestral graph is a new object. It's going to be like we have this notation here in brackets. So the G is any graph. So it's the bracket means a equivalence class of G. Okay, so it's kind of a notation that we sometimes write. So it's a graph with different edges. And this edge, so there are 6 types of edges. Sorry, I went. So there are 6 types of edges, either directed, like undirected, undirected, directed, bidirected. But there's also those with the circles, right? And first of all, P is going to have the same adjacencies of all the mags, because first the mags need to be with all the, since they are part of the same equivalence class, the first criteria is that they have the same skeleton. So of course the peg is going to have the same skeleton of all all its members. Then every time that I see a non-circle, so everything that's no circle, so these are no circle, no, this is a mag, sorry. So every time that I see a non-circle, it's going to be an invariance. So the peg is here. So these arrowheads here, they exist in all of them. First, because it's an unshielded collider, so you would have this. You will have more invariances. So for example, the fact that the X here is so this is also unshielded, but with X being a non-collider, right? So that's a definite non-collider. And there are more invariances that you can learn, not only these colliders with order, that we're going to see with some rules in the algorithm, but the fact that X is always an ancestor of V4 in all the mags, you'll be captured in this. So when you read a mag, you will know that it's you read a peg, you know that you can change circles with arrowheads as long as it's not forming colliders with order, right? And so for example, this can be an arrowhead into V, which would be this case here, because it's not a collider with order, right? This is not forming this is not a discriminating path. And everything that's in the peg, you'll be replicated in all members. So if I ask you, list a few mags that are part of this peg, basically everything that has no circle has to be here. So you have the same adjacencies. Everything that has no circles, you'll be here. So all the arrowheads or all the tails. And the circles, you have to respect first the idea that it's a mag, so we cannot have like cycles, almost cycles, and other stuff. And the direction is important. So for example, the fact that I don't have an example. You always have to check if X is actually an ancestor of V4, even through maybe like there is an inducing path connecting X and V4, while there is a directed path making X ancestor of V4. So you can create a lot of mags that are part of this peg by kind of using the definition of mag and these criterions that we learn. You get...
Is there anything preventing the V3, V4 edge being bidirectional in a mag, in this case?
V3 and V4
Yeah.
can be bidirected.
Okay.
That's exactly... No, but it can be.
Okay.
Yeah, if all edges in all graphs on top are bidirected. So
Nothing should break in the mag, in that mag.
yeah, I mean, for instance, if we had between V2 and X in all three mags bidirected graph, it would also be bidirected in the peg.
Yes.
No,
But
what I was saying is
is that here, right? You were
Here,
talking
I was-
about here.
because I only saw examples where they showed one, so directed, not bidirected. I was just wondering
Yeah.
if there was something I was missing, because
No.
I was thinking of potentially. Okay.
So you see that none of these colliders would be colliders with order, so you're not creating any collider with order. And even V3 and V4, right, in this triplet or this triplet. And it won't create any condition dependence, so you can definitely do it. And even the ancestralities, like it's not, sometimes you need to make sure that there is a path making, for example, X and V4 ancestral. No, that's not here. Yeah, but here it's fine.
So this peg is not possible if we have a directed path from V3 to X, right?
Directed path from V3 to X.
Yeah.
No, this would imply that V3 is an ancestor of X, and this is telling you that X is ancestor of V3, and V3 is a non-ancestor of X. There's no cycles.
Yeah.
So you could never even know how to create a cycle here, but you cannot create cycles. Okay. So another thing that helps is about this notion about definite triplets. I'm going fast here because it's pretty simple. Basically, the idea of definite non-collider is something that you look at a peg and you know that definitely there's no way to create a collider there. So first is an unshielded case. So in an unshielded triplet, you are certain that the variable in the middle, even though that is like circle, circle in y, into y is a non-collider in this triplet. It cannot be a collider. So when there is circle, circle, so that's a definite non-collider. Y is a definite non-collider in this triplet. Because because if it was a collider, this would be an invariance in the class, and it would be represented there, because it's right. So and that's a real representation of our class. So if it's circle, circle, it's because it's varying, but it's definitely not with the two colliders. The other one is when you have a tail, right? So y is also a definite non-collider in this triplet, although it's not unshielded, just because you have a tail on it. So you cannot form collider on y, right? This is not a case, right? So this is not a definite non-collider because it could be the case where y is a collider there, because you didn't have the way of representing invariances here.
Maybe for the first case on the left, we should be careful when we have this. We cannot use, for example, 2 bidirectional edge for x to y and y to z. We should be careful about when we want to extract, a mag from this one, for example.
If these two edges were bidirected,
it cannot be possible. Because then
it cannot be learned. It's not learnable yet. That's true. You have to be careful here. We are defining an object that says that everything that we are representing are objects that are equivalent according to condition dependencies. So these objects is not defined by if you include any other type of knowledge. So you are correct. If you have just these 3 variables, 2 bidirected edges here would be impossible to be representing just condition dependencies, because I don't have a way to know that x is with an arrowhead and the y is with an arrowhead. I only have a way to know that the y has an arrowhead, both arrowheads into it. But maybe you are in a situation where you are for sure you for sure know that x is a no ancestor of y. You know, for example, that this is something that came after it, so it's definitely a no ancestor. So you could add the arrowhead there and say that now we are representing a new class of equivalent modules, but it's no longer a Markov equivalence class. The definition of Markov equivalence class is only representing modules where you used only condition dependencies to represent the modules, right? So yeah, but maybe you see cases where people are defining a equivalence class, not a Markov equivalence class, where we would have this. And the collider is just a collider, right? So collider can just have 2 arrowheads on them. So if this has a circle, you are not sure if this is a collider. Okay? And we are going to use this idea to define what's a M separation in pegs. So we learned the separations in ADMGs, M separation in mags, and now M separation again in pegs. So you can actually apply M separation directly in the peg, not in the mag. to do this, we need to consider only paths that are called definite M-connecting path. So this path is a path where every non-endpoint vertex on it it's of a definite status. So all the triplets in this path is either a definite non-collider or a collider, right? Collider is always definite. Okay, so all the triplets in this path has to have a definite status. And then we are going to define as a M-connecting path if every definite non-collider on P is not a member of Z. So that's the same as this separation, right? So before a path is blocked if at least one non-collider is in the set, in the conditioning set. And here is just another way of saying that every non-collider is not a member of Z. So if I put at least one there, I will make it blocked. So just remember the same definition as before. So definite non-collider, if it's included in the set Z, makes the path blocked. Now every collider on P is an ancestor of some member of Z. So I'm defining M connecting. So if it's a collider, either the collider itself or any ancestor of it, so every collider on a path is either the collider itself is on Z, or another descendant of it is on Z. So the collider in the path is an ancestor of the variable that's in the Z. It's a tricky way of defining it, but it's the same intuition that you had before. But the only thing that changes is that we are now only considering definite status paths, or paths such that all the triplets have a definite status, either a definite non-collider or a collider. And then M separation is basically there is no definite M connecting path between them. So you need just to block all the paths that have definite status. So the example. So this is an example. There are three paths connecting V1 and V2. You see them? The first one is V1, V4, and V2. Is this a definite status path? Why not?
Because we're not sure about anything.
You are sure.
Oh.
That's unshielded, is the first case of a definite non-collider. It's an unshielded triplet. Idle is like circle, circle. This is a definite non-collider because it's unshielded. Got it? The other is symmetric, right? V2, V3, V1. Another definite status path. Now what about V1, V3, V4, and V2? So all the triplets have to have definite status. V1, V3, and V4. Is this a definite status triplet? It's shielded. So not. What about V3, V4, and V2? Again. So this path, I don't even look at it. Let's forget about it. So what's the set that separates, or M separates, V1 and V2? I just need to separate the definite status paths.
V3 or V4?
Perfect. Or no.
And you need both.
You
right?
need both.
For both.
Yeah,
the
yeah,
different
yeah,
paths
not
of
all
the-
and.
Yes. All of you are seeing this? what's happening, right? So basically, if I don't condition on both, I will have some dependence. So this is the only implied condition independence, and I check this by this M separation that looks only at definite status paths. What about this one? It's kind of similar. What's the set that separates V1 and V2? V4, just that? Yeah, just that. Why? Because that's a definite status path. The only triplet is a collider as definite, and I cannot condition on the collider, otherwise I'm going to open this path. The other path that's of definite status, similar to the first one there, is a definite non-collider triplet. So I need to condition on V4. And the third path is not of a definite status, it's the same thing. It's not, it's like this is not definite status, this is not definite status because it's unshielded. It's shielded, right? So if I do, for example, V3 and V4, I'm conditioning on the collider there, so I'm creating a dependence. If I just condition on V3, it's the same thing. Okay, what about this? If anyone knows from statistics instrumental variable, this is the IV graph. That is this instrument. That's just a curiosity. I want to know what separates V1 from V2. Let's start listing the paths.
V1, V3, V2.
This is the first path that's definite status. So V3 is part of the conditioning set. Now V3 is part of the conditioning set. What happens with the other path? Is of definite status.
No, but we can plug it with V4. No?
Is of definite status or not? Yes, it is. It's a collider. That's a definite non-collider. It's a tail here.
Yes.
So we need to look at this. So this is opening this path. So V4 is part of it, right? So this is an interesting case because we learned that this is a definite cause and this is an ancestral. So that is two tails in this graph. That's called IV graph. You'll see later. That's the implied independence. So I can condition on V3 and V4 to make independent. We have also this other independence here, right? It's a collider here, but that's it. That's all independences. This is just copying what's before. And from the peg, if you remember, I don't know if I listed or not, but we can list in this peg here, that was in the example before from this list of megs, those are all the implied conditioning dependencies using M separation on the peg. By definition, peg represents all modules, megs, that are implying the same set of condition dependence. So if you check later, exactly the same set is going to be implied by this all three, because those three are member of this class. And this would happen with any member of the class. So instead of, I don't know, maybe considering one module separately, each module separately, we can directly check what's happening in the entire class by applying this definition of M separation. Okay, I think that's done for pegs. We will start the FCI. It's a quick algorithm. I will get there. Any questions up to this point? It's a lot of definitions, but you get used to it. You see a lot of exercises, and basically with those definitions, you know a lot about learning or understanding graphs that are learnable from observational data, which will be the goal of the second part of the lecture. That's about causal discovery. Don't know if you have heard about it, but it's a hot topic today. So how about learning a causal diagram? So we don't know anything about the system. We want to do causal inference. You cannot just get the observational distribution. You saw this in the exercises comparing observation distribution. This is going to give you the wrong effect. So we need to know something about the underlying model, as the structure of the underlying model. Can we learn the causal diagram from observational data? What do you think?
I mean, I remember you saying parts of it.
Parts of it, perfect. So identifiability of the causal diagram in causal discovery is something that people study, but usually you cannot just assume that you have just observational data. You need to assume more. So you can, for example, say that your data comes from a linear model where all your error terms are non-Gaussian, and you have observed all the latent confounders, or you are under causal sufficiency. You are in a case where you have identifiability of the causal diagram. Some people do this. There's a method that's called Lingan. Maybe you see this in the literature. It's a famous method. But it's too strong. You have to say no unmeasured confounders, linear, non-Gaussian error terms. That's kind of weird, and not works. If you just want data and you don't want to assume anything else, you won't be able to learn the causal diagram. But you'll be able to learn the Markov equivalence class, or the PEG, which sometimes gives you information, as the IV graph that I showed you gives you information to identify the effect without knowing the true underlying causal diagram. So you learn that an effect is the same for all the members of the equivalence class. So it doesn't matter what's the method, the model behind it. It's just from data you can learn the pieces of the model, and these pieces of the model are sufficient to estimate the effect in the underlying model, because it's the same in all the models in the equivalence class. So that's the goal of causal discovery, is to learn a representation of the Markov equivalence class, if we are not assuming anything, which is the thing that we're going to see now. There is two types of methods. They are separated into constraint-based methods and score-based methods. We are going to see one example of constraint-based methods because it's based on condition-independence tests, not on a score, for example, a fitness of goodness score like BIC or something like this. Under unmeasured confounding, there are just scores when all your data are Gaussian, which is the BIC, Bayesian Information Criteria. There is also another score for discrete variables, but we are not going to mention. But in the presence of unmeasured confounding, the constraint-based methods are leading, and the most, or the standard one, is the fast causal inference that we're going to see it. So the goal is to learn the Markov equivalence class from observational data, right? There are a few assumptions. This is important to know. The first of all is that the observed distribution is the marginal of a distribution that satisfies the following three conditions, which means that we are going to assume that you have the observed distribution, and this observed distribution kind of can be estimated from data or not, but you have it, and satisfies the following. First, satisfies the Markov condition for some graph. So that exists a graph, which is the one that we are, the goal is to look for the equivalence class of this graph. So that exists is this graph G, such that all the separations in G are going to imply those observed condition independencies in P that you have in hand. You have P in hand. The other, so we are just saying that exists is G such that is an independence map, we saw this before. Sometimes we call it that P is semi-Markov relative to G if it's under latent confound. The other condition is called faithfulness. It's a very delicate condition. We are going to investigate this better next lecture. But assumes that everything that you have in hand is true in the true graph. So if you see an independence in your data, it's because the independence is really in the true model. So you don't have false independencies, you don't have false dependencies, right? It's kind of tricky. That's a very ongoing line of research, how to deal with violations of faithfulness to make their algorithm more robust. But for now, let's assume that we have data enough to make sure that everything that you observed there is not due to lack of statistical power or some statistical anomaly or something like this. Okay? If you want to estimate from data, especially from limited data, you need a condition dependence test. So if you don't have the P on hand, you have to get P hat, which is the one that you're going to extract from data. And to extract the P hat, basically you can just need the independencies implied in this independence by this distribution, right? So we need this condition dependency. So we assume that you have a good condition dependency test for your data. So if it's Gaussian, I think I have a list here. I'll go back to this list later. I just want to give you a few pointers. But for example, for Gaussian arrows and independent observations, you have partial correlation test. If you don't want to assume Gaussianity, I think it doesn't assume Gaussianity, but you have this kernel-based non-parametric test. Of course, it's you need much more data to so the power of a test when you have assumptions is higher than when you don't have assumptions. So if you're relaxing the parametric assumptions, of course you have lower statistical power, but you have this in case that you have a lot of data. This is one of the things, like this is an ongoing research. Like for example, if you have dependency across observations, you could, for example, create some condition dependence tests based on mixed models or something that deals with the correlations or the observations. But this is something that you assume that you have in hand. So there's a lot of tests available in the literature. You just need to look for the good one for your data set.
Excuse me, this, I don't know, extracting independence class, something like that, from observed data does not imply correlation instead of causality to this.
You're talking about dependencies versus
Yes.
correlation. Yes. So we are assuming that the test is indeed an independence test, right? And the alternative hypothesis is dependence, right? So dependence is the null hypothesis and dependence is alternative. So in cases where the data is Gaussian and linear, correlation is going to be exactly as independence. But for other cases, you need to actually derive an independence test, right? So correlation 0 doesn't mean dependence. This is what you're talking about, right? So, but for Gaussian, it means that.
No, I mean we are looking for causal, causality between.
Oh, no. This is just the building block of the algorithm.
Oh, okay.
We are going to need this to extract the independence.
Yeah.
We are going there.
Okay.
Sure.
Okay.
So the algorithm is going to do like this. We are going to have data on hand. Then, of course, you know that multiple SEMs could generate the data. So we don't know. This is in red because it's unobserved. But we have a way, that's why it's coming the condition dependence test. You have a way to extract all the dependencies and independencies that are in the data. And we are going to assume that they are true, right? Then I told you that you could play around and get the factorization. They are going to have many graphs that are implying the same thing, all the story that we talked so far. However, causal discovery is going to detect those invariances that we saw that could be learned. And algorithms that exist are, for example, the PC algorithm under causal sufficiency when you have no latent confounder. And the FCI algorithm, which is the one that I'm going to teach you now, doesn't assume causal sufficiency, so you could have latent confounding, and is going to be able to learn the representation of this Markov equivalence class, which is a PEG. So we are going to teach you this algorithm. It's not hard. So that's the pipeline. Basically, you start, so that's the unknown graph. You don't know it, but just for reference, keep it there. It was proposed actually in 2001, not this paper. And Gigi Zhang is the author of this paper. He proved in this paper a set of rules that shows completeness of the algorithm, which means that it's learning everything that's possible to learn from data. And it proposed 10 rules. He proposed 10 rules. Actually, it's completing the set of rules. So in the beginning, Spiritus proposed 4 rules, and then he proved the 5 to 10. Anyways, but the algorithm starts with the complete graph. Why the complete graph? Because the complete graphs tells you nothing, right? There's no invariance. There could be everything. And then you apply condition independence tests. You get these dependencies and independencies that you have in the data. Especially, you keep the independencies. For every independence, doesn't matter what's the conditioning set. For every independence, this is the first condition of a maximal ancestral graph. Remember that there is no edge, because you could find a separating set that separates both variables. This is what we're going to apply now. So every time that there is a pair that is independent, conditional to some set, doesn't matter the set, we're going to remove the edge between them. So X and W are independent, marginally, but doesn't matter. But there is no edge anymore, so we will remove the edge between X and W. So this edge here is no longer here. The same for X and Y. So we remove the edge between X and Y. This gives us the skeleton. Just this gives us the skeleton. Then we start applying the FCI rules. So it's a set of 10 rules. To be honest, that is the rule 0, so it's 11 rules. I should change there to rule 0. But then applying this rule from 0 to 10, we will get the PEG. I'm telling you now what are the rules after this. But this gives you the algorithm completely. And the idea is that it doesn't matter the order that you apply the rules. You just apply exhaustively until you cannot apply anymore. That's the way that the algorithm works. So you try to apply the 1, cannot. The 2, cannot. Oh, 3, I could apply. Now, after that, you start again, can apply the 1, the 2, and so on. And you apply one by one until you say, I cannot apply any of the 10 anymore, and then you're done. And if you're done, the algorithm is complete. That's the final PEG. The final PEG is correct and is representing the entire set of MEGs that represents this set of condition-dependent sets that you used here to create the skeleton. Okay? The meaning of the PEG is this thing that we know. So arrowheads, no ancestrality, tail ancestrality, circle, no invariance. So there's the algorithm also can deal with selection bias, so you can learn undirected edges in this. So selection bias will be represented by undirected edges, and spurious association where neither A causes B or B causes A is going to be represented by directed edges. Yeah, so that's just a few examples. I'm going to give you one example. I think I have a few minutes. I think it's sufficient. Let's see one example where we apply the rules, and then at home you see the proof of them. I have in the end a few slides showing the proof of them. I will leave you this for home. It's very simple, the proofs, by the way. But first of all, we form the complete graph, right? So suppose that this is our unknown. We don't know it, just for reference. But I have 5 variables. The first thing is to connect every variable with a circle S. And second step is to find the separating sets for every pair. There is an efficient algorithm for finding this. I will explain this later. For now, assume that you have a good efficient method to find the separating. You could go one by one in a grid search, but this is inefficient. But every pair that you find a conditioning set S12 that separates V1 and V2, you're going to record it there and then remove that. So in this example, if you look for these separations here, you would know what are the sets, and this will be here. But we have data, and we are using a condition dependence test to find this, right? So we don't know that, but you can check. V1 and V3 will be independent given V4, and this is removing our edge between V1 and V3, which is in red. V4 and V5 are independent given another conditioning set here. That's why we are removing the edge between V4 and V5. So this is our skeleton. This ends the first step. Now, that is this rule 0 that I told you. The rule 0 is finding the unshielded colliders because they are easy. So there is this idea of finding all the colliders that are given, that are from unshielded triplets. So for every unshielded triplet, so in our example, this is here. Oops. Here. We are here now. That's the skeleton. There are some triplets that are unshielded. For example, V1, V2, and V3. There is no edge between V1 and V3, right? V4, V2, and V5, the same. And for all these unshielded triplets, we have to check what's the separating set of it. Because if the variable is part of the separating set, it's a non-collider. And if it's not, it's a collider, right? So we just apply this idea. And if you remember, those were the tests. So V2 for V1 and V3 is just V4. V1 and V3 is just V4. So this triplet, V2, is not part of the conditioning set. So we put it as a collider. The other one is V1, V3 is also a unshielded collider here. It's forming here unshielded triplet. Since V5 is not part of the conditioning set, it's an unshielded collider. Okay, so we learn all the unshielded colliders by just checking triplets that are unshielded and checking if it's part of the variable is part or not of the separating set. Now it comes the 10 rules. The first rule, this is just some references that I told you. So the 1 to 4 and the 0, they are kind of complete, but just for arrowheads, for no ancestrality. Then Zhang proved all the others, including selection variables. So those are references if you want to take a look later. But going back to the example, we were here, right? Then there are 10 rules. As I said, there's no order. You just check what's the available right now, and sometimes you can apply more than one, but you just pick the first, and this doesn't matter. In this case, I'm going to apply the 3 because it works. So the 3 tells me that if I find that pattern in the left top part here, I can change the circle in V2 to an arrowhead. Why? Is because V4 is part of, it's a non-collider, so it was part of the conditioning set. So V4 can never be a descendant of a collider, otherwise V1 would be not separated of V3 by conditioning on V4. So I know for sure that V2 is a non-ancestor of V4. This is in the proof, but that's the type of reasoning that we're going to see in the proofs. Basically by excluding, by contradicting the cases that you did before, like you know already that this is a non-collider from the previous case, because the rule 0 is the first thing that you do. It has to be the first. So all the other steps, for sure, knows that every unshielded triplet with circle circle is a non-collider case. So in this case, if V4 was an ancestor of V4, then it would open the collider V2, and this would not be separate. You can think it later.
What is that symbol?
Anything. Yeah, this is like a wild mark. Doesn't matter what's there in the situation of the algorithm. That's why I put this asterisk. Because in the algorithm, you are applying the rule 3 in some steps that maybe you already learned these edges. So that's the way that they define the R3. So you know for sure that there is a circle in the edge here. But this could be a circle, this could be an arrowhead, could be a tail, because you could learn before in the algorithm. So you don't know any. This is going to be the same, so you don't change, but you change the circle to an arrowhead. That's what's changing with the rule here. And in the question?
So just to make sure I understood correctly. So the reason we know there's a path from from V4 to V2 is that the fact that we condition on V4 doesn't or leads to contributes to an independency, or doesn't lead to a dependency we know can be a collider or a descendant of a collider.
Kind of. So the edge is there because you couldn't find any conditioning set that separates them. So that was your question. But the fact that I'm adding an arrowhead into V2 in this edge is basically you try all the possibilities. Suppose that is a tail there. If it's a tail there, it cannot be a tail on V4, because then it would contradict the case of having arrowhead into a pair of variables that has tail, that has an erected edge. So it's not a tail. So it's not a undirected edge. Could be a directed edge from V2 to V4. So there is a tail, but could be with an arrowhead into V4. That's the other possibility. Why this would create a contradiction?
Yeah, and so it would create a contradiction, as it would lead to a dependency if we had.
You need to now go back to the fact that V4 there is a circle. When you apply the rule 0, you converted all the unshielded triplets to colliders or non-colliders, or leave it as non-colliders. So the fact that it's not a collider there means that V4 was part of the separating set between V1 and V3, right?
Yes.
So this is known, otherwise it would be a collider. Since V4 is part of the conditioning set, you have a collider on V2, what would happen if V4 is a descendant of a collider?
It can't be part of the separating set.
It cannot be part of the separating set. So it's a contradiction. So you excluded the two cases where V2 has a tail, cannot be an undirected edge, and cannot be a directed edge from V2 to 4. So for sure you know that's an arrowhead. All the proofs are like this. They have like 3 lines. They are kind of very simple. You read later. But basically what you have to do now is look at the rule, the pattern there, and see if you can apply. And you can apply in this case because V4 is exactly the thing there. And you orient this circle into this because V4 was part of the conditioning set. Then there is this other rule, that is the rule 1, that tells you that if you already have this arrowhead into V2, then for sure you can orient V2 pointing to V3. So you learn both here, the tail and the arrowhead. You could have the arrowhead before there because there is this wild mark. But for sure, V2 is going to be a cause of V3. And this is going to be applicable here. So you have, for example, V1 and V3 cannot be adjacent, right? So that's the situation. V1 and V3 are not adjacent, so it's an unshielded triplet, and there is an arrowhead into V2. So we have here a case, right? So V4 was pointing to V2, and this is exactly this formation. You can check the proof later. It's very simple as well. Let me just finish, and maybe I can come back to help you with the proof. So this is what we have after 0, 3, and 1. Now that is this rule 4, which is the discriminating path. You know already. If you look at our graph, the current status of our graph, there are some discriminating paths. Maybe you can help me to find. So it's a collider path where all colliders are parents of the last variable.
V1, V2, V3, V5?
V1, V2, V3, V5.
Or no, maybe V4, V1, V2.
No, that's correct.
That's correct.
Yes, it's kind of,
Oh, yes.
because this is a collider, this is a parent of the last variable, so this is discriminating. This is the discriminating path for V3. And what you have to do, oh no, it's not, because it's not separated.
Yeah.
Yes. Okay, sorry.
So V4, V2, V3, V5, or?
Yes. Because V4 is separated from V5. That is this collider path where the collider is parent of it. So this collider, this discriminating path tells me what's the status of this triplet. And we just need to check if V3 was part of the separating set of V4 and V5 or not. And I guess it's here. So V3 is part of V4, separating set of V4 and V5. So for sure, this is a non-collider, and I know more, so you can check the proof. That is going to be, we kind of discussed even in the lecture, we know for sure that's going to be from the variable that's been discriminated to the last variable. So we have a tail here. That's what I learned. That is another one, it's symmetric. It's here, to the other side, where we discriminate the tail now here. Okay, that's our final peg. So you apply just this set of rows. So it started with the skeleton, then 0, 3, 1, 4, and 4 again. And then you got this. And this is what you have. That's the Markov equivalence class of the set of condition dependencies that you learned. That's this one. So if you check it by the separations, you have this. If you check by M separations, you're going to have exactly the same. Okay. There are more rules. I will stop here, but you check. Those are the proofs. So for example, for the rule 1, I have here the proof, the sketch. Basically, since all colliders were oriented before, you know for sure that V2 is not a collider. So it has to be a tail, and you cannot have like an undirected edge, otherwise you would violate the idea of maximal ancestral graphs. So it's for sure an arrowhead. So that's what's written here. So you just check at home. If you have questions, you can ask me next lecture. But you have the rule 2. So basically that is a pattern, and you can convert to something else. And all the proofs are here. There's 3, 4, and so on. Yeah, that's a lot. But so I recommend you at least to learn by heart the rules from 0 to 4, because this is what we usually do in Prezi, and in Prezi, I mean in my exams and the exercise sheet. But you need to know that there are 10 rules. They are all necessary to have completeness of the algorithm. And if you run the algorithm, you kind of know that all of them are implemented there, and basically looking for patterns and applying the rule. There's nothing crazy. Okay, so So they are all here. That is also this example just for me to say that, okay, I use the rule 9. So you can do at home. Basically, it's going to apply the rule 0, 1, 2, 4, and then the rule 9. So sometimes the other rules are necessary. This is one example where you use it. So basically, those are the independencies are implied by the ADMG and the PEC. They are the same. Okay, that's all for now. We have an exercise about causal discovery. It's already online. But I have some readings, especially this paper by Gigi Zhang. If you're interested in the theory, I really recommend you. It's a pretty nice paper, and you have already the definitions necessary to read it. You know all of that. That's the book where the algorithm was first proposed. So it's from 2000. So if you need like more, I don't know, more like a touchable way to learn the algorithm, you can read this chapter. Yeah, that's it for now. Thank you. You have the exercise session with Jan.